Shripad Patil, go ahead. Shripad, you here? You want to turn on your video?
Yeah, sorry, just give me a second.
Mm-hmm. Yeah, there you go. Go ahead.
Let me share my screen. Can you see that?
Yes, go ahead.
All right, so my topic was using nanoparticles. Hello, sorry. Sorry, I heard someone say something. Anyway, my topic was using nanoparticles to treat Alzheimer's and how it could increase the field of treatment that we have right now and how it could revolutionize how we deal with Alzheimer's and how we deal with people who have Alzheimer's. So first, a little bit about me. My name is Shripad. I am in the 11th grade at Blaine High School in Blaine, Minnesota, and I'm interested in biomedical engineering. So what is Alzheimer's? Well, Alzheimer's is a neurodegenerative disorder, which essentially means that it's a disorder that physically affects the brain's size and the brain's function. It's the most common form of dementia, and its symptoms are like declining cognitive function because you physically don't have the connections that you would typically use to think and reason, stuff like that. Memory loss because you're losing the places where the memory is stored, and then behavior changes because parts of your like frontal cortex and stuff like that, where that would typically control your behavior and how you act, are degenerated, thereby meaning that they can't function as they are intended to function. I got this information from the research paper on Young et al., published in 2021. So let's first take a look at what this diagram, and let's see what Alzheimer's actually does to the brain. So I want you to notice a few things on the left here. First of all, the cerebral cortex, which is that little darker part on the outside of the brain, is healthy looking. It's not shriveled at all, and it's the right size, everything like that. Another thing is that the sulci, which are these little like branches of the brain, are all not shriveled. They're the proper size, proper function, stuff like that. Finally, these holes in the middle are called ventricles, and they are also the right size. And again, not shriveled, not enlarged, nothing like that. On the right side, with severe Alzheimer's disease, you can see the cortex of the brain is shrunk, which means that any connections that were in that part of the brain are no longer working as intended, as they might have deformed or they might have disconnected entirely. Then the hippocampus, which is a major thing in your brain for like decision making and also like automated processes, is shrunken as well, thereby meaning that that part of your brain or that part of your function is also impaired. Finally, the ventricles in every brain are enlarged, thereby which pushes out to the side any connections that you may have had there, once again impairing function. If you look on the side, this is like a close-up view of how your nerve cells actually look. This looks healthy, where all your connections are properly attached, and your cells are, not lysed or anything like that. On the right, you see your nerve cells are damaged and dying. You can see that there are disconnections within here. And also you have these things called tau tangles, which are shriveling your nerve cells and damaging them. And also these things called amyloid plaques, which also are present and help contribute to the degeneration of your brain. So let's talk about treatment strategies. As of right now, what's happening is it's mostly what's called palliative care, which is essentially where you try to alleviate the effects of the disease rather than alleviating the actual disease process itself. So there are things called acetylcholine esterase inhibitors, which increase your levels of acetylcholine, which are neurotransmitters within your brain. These can only mildly help your cognitive function, and they're not very effective. Along with that, there are things called N-methyl-D aspartate or NMDA receptor antagonists, which also regulate glutamate, which is another neurotransmitter. And this one helps more with behavioral symptoms that may be caused by Alzheimer's. As far as other things go, as far as treatments that are not medical or like not medicine-based go, there's cognitive stimulation therapy, which is essentially engaging your patients in different activities that will help them to regrow potential connections that may have been broken. Behavioral interventions, which are strategies to just ease the symptoms of Alzheimer's and to make sure your behavior doesn't go out of check too much. And then finally, caregivers are mainly also providing palliative care and making sure that these symptoms are like trying to cushion the symptoms that are caused by this disease. And again, this research was pulled out from the paper by Yiannopoulos et al. In 2020. So let's talk about the research goals. So first of all, I asked two questions. Is Alzheimer's treatable with the greater access afforded via nanoparticles? And what nanoparticles could work for this drug delivery? This research is important because it's important to try to reverse the effects of Alzheimer's rather than just trying to accommodate for the actual effects of the disease, so symptoms of the disease. So first, let's look at what nanoparticles afford us to transport across the blood-brain barrier. So what the blood-brain barrier is it's a big roadblock in the way of transferring drugs to the brain, as it is essentially a shield for the brain to make sure no foreign substance can get in. So it's a good thing if you have like viruses and whatever else, so that they don't go into the brain and damage your brain further. But it's not a good thing if you want to put in like drugs and other treatment into the brain, as it means that you cannot effectively bring those drugs in without a carrier molecule or something of that sort. So this information was derived from Shripad et al. From 2016. So basically, there are a few ways where nanoparticles can transport across the blood-brain barrier. So typically in disease processes like Parkinson's and Alzheimer's, you have these called epithelial cells. These are normally in the brain, but these junctions here are called tight junctions, where the cells are smushed together essentially and nothing can pass through. In disease processes like Alzheimer's and Parkinson's, these can open up and become loosened and damaged, allowing anything to pass through, which means that you could have nanoparticles passing through there as well. Now, this is not ideal because I mean, you just don't want to rely on that because you don't know if these are like this damage actually has occurred, and you don't want it to get to that point. Now, another way for it to work is receptor mediated. Receptor mediated transfer, which basically the nanoparticle will bind to a receptor on the surface of the epithelial cell, and then it will be carried through the cell on what's called a vesicle, which is essentially where part of the phospholipid bilayer that surrounds the cell basically coats the drug or your nanoparticle and brings it to the other side, allowing it to go through without being allowing it safe transport through. And then finally, there's one called adsorption, which is using like chitosan, albumin, which are two natural nanoparticles. But what this does is essentially these are positively charged particles, and because the phospholipid bilayer's heads are negatively charged, these as they get closer, they're attracted to the head of the phospholipid bilayer, or the layer that surrounds the cell, meaning that as they get closer, they start to form an indentation into the cell. Then as they continue through, again, the cell surrounds them in what's called a vesicle, thereby protecting the nanoparticle and whatever else drugs you have on there. And then they get to the other side and you can release your drugs and other factors. And some of these methods can be combined on certain drugs. So it's not just like, oh, you can only, this nanoparticle is only restricted to one thing. So let's talk about effectiveness of different nanoparticles. So this was again derived from the same paper of Shripad et al. So basically what they did is they studied the effectiveness of certain nanoparticles and drugs used in different rats, mice, and other clinical trials to see how their uptake into the brain was, as well as their effects on the actual brain itself. So first of all, there's PLA, which is, you may know it from like the plastic, it's polylactic acid. So this was used with what's called a neuroprotective peptide. And what this basically did is it helped with so first of all, the PLA meant that there was an enhanced drug accumulation in the brain, which is a good thing because you want more of the drug to get into the brain and be able to treat more. So ameliorated here just means that it made them better. So basically, any learning impairments that happened because of nerve damage from your amyloid beta plaques and stuff like that were made better because they're protected by, or the nerve endings and et cetera were protected by the drug. And other issues with like neurons, neuron loss, stuff like that, disruption of certain important neurons were also alleviated slightly. Another thing was PBCA, which is poly-N-butyl cyanoacrylate. When combined with NGF, which is a nerve growth factor, got uptake when put into a rat brain, which had amnesia. It reversed the amnesia that the rat had and improved the recognition memory because, again, it is growing back the nerves that were once lost. Now, PLGA, the next one that they were using, which is polylactic co-glycotic acid, when combined with coenzyme Q10, had very good uptake to brain regions, namely the cortex, which is this part again, the paracoli, the third ventricle, which is somewhere around here, and the choroid plexus epithelium. So this reversed any behavior performance that happened because it specifically worked to reverse the damage to parts of the brain that control a behavior of this, in this case, mice or rats. Finally, the last one was N-butyl 2 cyanoacrylate, or BCA, used with chloroquinol, which is originally a drug to treat like fungal infections, I believe. So what this did is what's the good thing about this is it specifically targeted those beta plaques or amyloid beta plaques that are so prevalent in the Alzheimer's disease process, both in all the trials that they used, and they had a really high brain uptake and retention, which means that the drug has a more effective time in the brain before being discarded. And another big benefit with this drug is that it provided a good working base for imaging, which means that you can more easily track the drug's process or the drug's progress inside the brain of, in this case, mice, but ideally humans in the future. So another potential solution for this is liposome-based delivery. So basically, this paper was Yamaguchi et al. In 2020. What they did is they basically attached a ciclet peptide that looked like this to a what's called a phage or a bacteriophage. So it's basically a small particle or small not particle, but it's a small organism that they bring into the brain to test the effectiveness of these peptides. So basically what the benefit of this is that, so here if you can see, it says 1 micrometer is the phage size, all right? And the liposome is 150 nanometers. Now, 1 micrometer is 1,000 nanometers. So if a phage of the size of 1 micrometer can make it through the blood-brain barrier and get into the brain, then that means that a liposome, which is significantly smaller, right, will have an even easier time to get into the brain through the blood-brain barrier. A bigger benefit with using this as well is that since your drugs are contained within a little vesicle that is made by that phospholipid bilayer, there's a bigger variety of drugs that you can use, and also you can import more drug into the brain per nanocapsule liposome as compared to certain nanoparticles. So to conclude, the questions that I answered is Alzheimer's disease treatable with the extra access afforded by these nanoparticles and liposomes? Yes, drug delivery is possible, proven by these rats and mice trials in the lab, and it's effective. Now, the nanoparticles that could work vary depending on what specific drug you're using, what areas you're trying to target. Like, for example, if you're trying to target your plaques, you're going to use the one that goes for plaques. If you're trying to target the ones you're trying to target vesicles or behavior-related things, you go for the one that was targeting behavior-related things. But based on the criterion that I looked at, the best one right now looks to be N-butyl 2 cyanoacrylate, again, because of the benefits with imaging, as well as the uptake and specific targeting of the plaques. So the contribution that I made is the centralization of this data and all this information that is currently available on the transmigration of the blood-brain barrier for treatment, and selecting the best current methods for this treatment, and also explaining them. So some limitations is due to lack of access of equipment or finances to work on nanoparticles. All of my results were based on research that other people did. Now, obviously, ideally, you'd like to do this research for yourself, to trial these for yourself, and to understand if this really actually does work and how it would work. But because I don't have the access to the facilities or the finances for that, it's not possible. So ideally, that would happen but we can do that. So finally, I'd like to thank Coach Joe, Coach Virgil, and Dr. Lova for their unending support through this process. Coach Virgil, I was gone for a lot of his classes, and yet he still helped me a lot through my paper and helped me to understand like how to write specific parts on my paper, because that's something I struggled with before. Dr. Lova helped me a lot by providing me different resources to or different papers and paper examples to use in my paper, as well as different like resources of past research that I could use as well. And I'd also like to thank my parents for their help in both keeping me on task, but also their unending support of my work. Thank you so much.
My mute doesn't work immediately. So awesome, Shripad. I mean, we all had to, especially me, I had to pinch myself and remind myself that this was a high school student presenting, not some expert. So a big round of applause to you. The depth at which you've gone and your passion for this specific topic is like commendable. So awesome. Okay, so Dr. Lilova, any question for Shripad?
Yes, very impressive work. So my question is a little bit the next level. So all of these nanocarriers you read into and you look into, do you think that they also can be used for other similar diseases which require passing through the blood-brain barrier?
Oh, for sure. Yeah. That's why I mentioned like Parkinson's and whatever else at the start when I was talking about disease processes, because those also are neurodegenerative disorders that affect the actual brain structure. And so with these nanoparticles, especially the ones that target not just the plaques or stuff that's specific to Alzheimer's, if you look at the ones that have like the nerve growth factor and other neuroprotective agents, if you use those drugs in combination with the nanoparticles that specifically target areas where those will be useful in the brain, that would allow for other diseases like Parkinson's and other brain diseases to be treated more effectively. And so it's not specific just to Alzheimer's, but Alzheimer's is the disease I took as my main inspiration for this research.
Thank you. Great.
Thank you.